by putting you and everyone listening right on the spot. I have a challenge.
Well, I love a good challenge. Let's hear it.
So stop what you're doing unless you're driving, in which case keep your eyes on the road and try to solve this in your head right now. Think about the three massive industry-level engineering problems that essentially birthed modern data science.
Right, the big three.
Yeah, the big three. First, detecting fraudulent credit card transactions in milliseconds out of millions of swipes. Second, looking at a medical scan and diagnosing a subtle disease faster and more accurately than a human doctor. And third, the one we are really going to drill into today, valuing real estate with thousands of variables.
That third one is the classic jumping off point. It really perfectly illustrates the core engineering problem.
Exactly. So here's the thought experiment. Imagine I hand you a list, a massive, heavy list. It contains the history of 10,000 past house sales in a major city.
Okay, so I've got the historical data. 10,000 examples of pure reality.
Yep, you have the ground truth of the market. I give you everything. The square footage, the number of bedrooms, the neighborhood quality score, the year it was built, the size of the garage, and exactly how much each house sold for, down to the penny.
So I have the inputs and I have the final price.
You do. Now, here is the challenge. I give you the details of a brand new house that just hit the market 5 minutes ago. Same city, same exact type of data points. It's got the square footage, the bedroom count, all of it, but I do not tell you the price.
Ah.
Can you predict it?
That is the fundamental question that drives this entire industry, isn't it?
It really is. And naturally, if you're a traditional programmer or just someone who prides themselves on, strict logic, your brain immediately goes to one very specific way of solving this. You start thinking about rules. You start building a calculator in your head.
Right, the classic if-then approach. This is how we've built software for the last, 40 or 50 years?
Pretty much.
You sit down with a giant cup of coffee and you try to hand code the logic of the universe. You write, if the area is greater than 2,000 square feet and the location is downtown, then the price must be high.
Exactly. You're building this massive decision tree. If it has a pool, add $50,000. If the roof is leaking, subtract $20,000.
If it has a two-car garage, add $10,000. It feels intuitive. It feels controllable.
It does feel controllable. But here is where that totally falls apart. And I think this is where traditional software engineering hits a brick wall. What if the house is huge? It has a pool. It has a 3-car garage.
Sounds expensive.
Right. But what if it's right next to a noisy 8-lane highway and the school district was just rezoned to a significantly lower rated school?
Oh, well, then the price tanks. Or what if it's tiny, right, like a small house, but it has historic Victorian architecture that people in that specific zip code pay a massive premium for just because it's charming.
Exactly. Suddenly, your nice, neat list of rules isn't 5 lines long anymore. It's not simply pool equals plus money. It becomes pool equals plus money unless it is winter, Andy, the pool is cracked. Or the neighborhood is primarily retirees who hate doing maintenance.
Right, your code just explodes. Suddenly, your list of rules is 50,000 lines long. You are literally writing exceptions for your exceptions.
And the moment the market changes...
Oh, forget about it. Say interest rates go up or a new tech factory opens in town, your entire massive rule book is instantly garbage.
It's incredibly brittle. It's essentially impossible to maintain at an industry level.
And honestly, it's a bit arrogant. It assumes that you, the human programmer, know exactly how every single variable interacts to impact the price. It assumes you can calculate the interaction between hardwood floors and the distance to the nearest coffee shop in your head.
And let's be real, we absolutely can't. That level of complexity is just way too high for human logic to hard code. And that failure point, that exact wall you hit that is where the paradigm shift happens. That is where we stop doing traditional programming and start doing machine learning.
That is the big pivot.
Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry ready and apply your knowledge to real industry projects.
It's great to be here doing this deep dive. We are going to go really deep today.
We really are.
Yeah.
I talk to so many people who want to break into this field. They know some Python, maybe they've dabbled in basic scripting, but when they hear experts talk about AI, it honestly sounds like a completely different language.
Oh, absolutely. It's all hyperparameters and stochastic gradient descent and neural architecture. It sounds like sci-fi gibberish to the outsider.
Yeah.
It's basically gatekeeping by vocabulary.
It really does feel that way. So our mission for this deep dive is to completely cut through that fog. We are going to build a mental model. We aren't going to look at complex math today. We aren't going to stare at code. We're going to look at how AI actually thinks.
That's the perfect goal.
Mhm.
By the end of this conversation, we want you to be able to look at a complex, real-world problem and break it down into the core components: data, pattern, prediction. We want you to decode those expert-level sentences that currently intimidate you.
So let's start with the vocabulary itself. Because even the biggest buzzwords get used totally interchangeably in the media, and I know that drives engineers absolutely crazy. AI, machine learning, deep learning, are these just fancy synonyms for cool robot stuff?
It happens all the time. You see them in news headlines, in startup marketing copy, and they were treated as the exact same thing. But if you want to actually be industry ready, you have to know the hierarchy. You have to understand the taxonomy. Think of it like a set of those Russian nesting dolls.
Okay, I like that visual. Let's unpack this. Start with the biggest doll, artificial intelligence.
AI, or artificial intelligence, is the broad, overarching goal. It is the umbrella term. It simply means making machines behave intelligently. That's it. It's a very wide, almost philosophical definition. If a machine does something that looks smart, whether it's playing chess, recognizing your face on your phone, or recommending a movie, that all falls under the big bucket of AI.
So let me challenge you on that for a second. If I write a really complex if-then program, that brittle, awful code we talked about earlier, and it plays tic-tac-toe perfectly, is that technically AI?
Yes, technically it is. We often call that symbolic AI, or good old-fashioned AI in the industry. It's behaving intelligently. Think of the smart assistant analogy. You just want a system that acts smart.
Mm.
That's the what. It really doesn't matter how it got smart, just that it is smart. So AI is the destination.
Okay, so AI is the destination. It's the final result we want to achieve. Now, open up the doll. Where does machine learning fit inside that?
Machine learning, or ML, is the how. It is a specific subset of AI. Remember how we talked about not writing those brittle rules, but instead showing the computer examples?
Yeah, giving it the 10,000 house sales?
Exactly. That is machine learning. It is the method of achieving artificial intelligence by teaching a computer from data rather than programming it explicitly with rules.
So to clarify for everyone, all machine learning is AI, but not all AI is machine learning.
Got it. Just like all squares are rectangles, but not all rectangles are squares. ML is the method of teaching with examples. It's the statistical approach. It relies on probability and finding patterns in data rather than rigidly following human-written rules.
Okay, so we have the broad goal, which is AI, and the method, which is ML. Now, open the doll one more time. What about the term that's literally everywhere right now, usually attached to generating wild images or ChatGPT deep learning? Is that just extra good machine learning?
In a way, yes. Deep learning is the specialized tool inside the ML method. It's a very specific technique within machine learning. It involves using multi-layered neural networks, which are algorithms inspired roughly by the structure of the human brain, to learn incredibly complex, subtle patterns.
Why do we even need a special name for it? Why isn't it just called advanced machine learning?
Because of the nature of the data it handles. Standard machine learning is absolutely fantastic for spreadsheets like our house price list with columns and rows. It eats spreadsheets for breakfast. But if you want a computer to understand a photograph or a recording of human speech,
Those don't fit neatly into a spreadsheet column.
exactly. A photo is just a massive grid of thousands of individual pixels. The patterns in a photo, like the curve of a cat's ear or the specific texture of a dog's fur, those are incredibly subtle and complex. You need layers upon layers upon layers of processing to extract those specific features. That depth of processing layers is exactly why we call it deep learning.
I really like the analogy of a power tool here. If I'm just hanging a picture frame in my living room, I might just need a simple hammer that's standard machine learning. But if I'm drilling through 20 feet of reinforced concrete to build a skyscraper foundation, I need the industrial heavy-duty jackhammer. That's deep learning.
That's a perfect way to view it. And for our deep dive today, we're going to focus firmly on that middle layer machine learning. Because if you understand the core logic of ML, deep learning is really just a scaling up of that exact same logic. The fundamental principles, data, training, testing, are exactly the same across both.
So let's go back to our main house price challenge. We've established that we want to use machine learning. We want to show the machine examples instead of writing rules. But showing examples honestly sounds a bit vague. How does it actually learn from them? Because I know there are different styles of learning in the industry.
There absolutely are. And the two main ones you will hear about constantly in every tutorial and every job interview are supervised learning and unsupervised learning.
These literally sound like parenting styles.
Yeah, essentially are. Let's look at the house price case study again to break them down. In that scenario, I gave you a massive list of houses,
Yeah.
right? And critically, I gave you the final price for every single house.
Right. You told me this house is 2,000 square feet, it's in this zip code, and it sold for exactly $500,000.
That is supervised learning. The absolute key here is that you provided a label. You gave the system the answer key. You said, here are the features, the area, the rooms, the location, and here's the correct answer, the price. The model looks at the features, makes a guess, checks the answer key, sees how horribly wrong it was, and then mathematically corrects itself.
So supervised learning is basically like being in a classroom where the teacher gives you a math worksheet, you fill it out, and then the teacher immediately marks it in red pen and says, no, this one is wrong, here is the right answer, try again.
Exactly. You are literally supervising the learning process by providing the ground truth. This is by far the most common type of ML deployed in the industry right now. Predicting retail sales, diagnosing diseases from x-rays, filtering out spam emails. These are usually supervised because we have vast amounts of historical data with the correct answers already attached to them.
But wait, isn't that incredibly hard, getting all those answers?
It is the single biggest bottleneck of the entire AI industry. Getting raw data is easy. We generate petabytes of data a day. Getting the labels is hard. Someone, usually a human being, have to sit there and confidently say, yes, this x-ray has a tumor, or yes, this image contains a stop sign. That's exactly why you see humans constantly doing those KPT-CHA tests online. Click all the traffic lights. We are literally doing free labor, creating labels for someone's supervised learning model.
That is wild. So supervised learning is incredibly powerful, but it's expensive because you desperately need those human-verified labels.
Correct. Labeled data is the gold standard, but mining that gold costs a lot of time and money.
So what on earth is unsupervised learning then? Do we just literally not give it the answers?
Precisely. Imagine I give you that exact same stack of 10,000 house records. I give you the square footage, the number of rooms, the location, but I delete the price column. I just wipe it out entirely. And I hand it to the machine and say, go learn something useful.
What can it possibly learn? It has no idea what a house is worth anymore. It can't predict a price.
No, it absolutely can't tell you the price. But it can look for hidden structure. It can look for patterns of similarity. It might crunch the numbers and say, hey, I noticed that these 2,000 houses are all huge, they all have pools, and they're all clustered in this specific suburban zip code. I'm going to group them together into a bucket. And then it says, these other 3,000 houses are tiny, have no yard, and are in the city center. I'll group those into a different bucket.
So it's just organizing the data. It's clustering it.
Yes. It's exactly like dumping a massive bucket of mixed Lego bricks on the floor and asking a toddler to sort them. They might sort them by color, or they might sort them by shape. They don't know the word red or the word rectangle. They just intuitively know that this brick looks like that brick. That is unsupervised learning, finding hidden structures and groupings in completely unlabeled data.
Give me a real-world industry example of this, because I get the house grouping thing, but who actually uses this to make money?
Think about credit card fraud detection. That was one of our hook problems. Sometimes banks use supervised learning because they have a database of transactions that they know for a fact were fraud. But sometimes, clever scammers invent entirely new techniques that the bank has never seen before. The bank has zero labels for these new attacks.
So how do you catch a scam you've never seen?
You look for weird, anomalous behavior. If you, the customer, usually spend $50 a day on groceries in Chicago, and then suddenly, within 10 minutes, there is a $5,000 purchase for electronics in Paris that aggressively stands out. The system doesn't necessarily know for a fact it's fraud. It doesn't have a label for it, but it mathematically knows it does not fit the cluster of your normal data.
Yeah.
It's an anomaly.
So it's playing the game of one of these things is not like the others.
Exactly. Or think about Netflix recommendations. They might not know exactly what specific microgenre you like, but they see that your viewing history closely matches user group A. So they just recommend whatever user group A is currently binge watching. They're clustering you with similar people. They don't need to know why you like it. They just need to know you belong in that behavioral cluster.
That makes total sense. So to quickly recap for our mental model, supervised is, here is the input, here is the target output, learn the map between them. Unsupervised is, here is a giant pile of raw data. Tell me how it structurally relates to itself.
You've got it perfectly. And for our specific deep dive today, predicting those house prices, we are firmly operating in the world of supervised learning because we want to predict a very specific numeric target, the final price.
Okay, let's get visual. One thing that really helped me when I first started looking at this stuff was completely moving away from the abstract, cloud-like idea of data and actually visualizing what the machine physically sees.
This is such a crucial step for beginners. When engineers talk about datasets, it sounds very fancy and intimidating, but I want everyone listening to just visualize a simple, boring Microsoft Excel spreadsheet.
Just a standard grid, rows going down, columns going across.
That's it. That is your dataset. Now let's break down the exact anatomy of this spreadsheet because there is very specific terminology here that you absolutely need to know if you want to understand the industry literature.
Okay, let's look at the rows first. In our 10,000 house example, what exactly is a row?
Each horizontal row represents one specific individual example in the real world, one single house sale. In the industry, we often use the lowercase letter m to represent the total number of rows. So if you have 10,000 houses, m equals 10,000.
Okay, M is the count of examples. Now what about the columns?
This is where we have to split things up carefully. The columns like square footage, number of bedrooms, zip code, these are called your features. They are the inputs. They are the clues that a detective uses to solve the mystery. We usually say we have M features.
So if my spreadsheet just has area, rooms, and location, N equals 3.
Correct. But there is one very special column, usually the very last one on the right.
The price column.
The price. That is not a feature. That is the label, sometimes called the target or the Y variable. That is the actual thing we are trying to predict. So when you look at that spreadsheet in your mind's eye, your brain should automatically draw a thick line down the page. Everything on the left is features, which is the input, and that one single column on the right is the label, which is the output.
So mathematically speaking, and we promised no heavy math today, but just for notation's sake so people can read the docs, the shape of the data is just written as MN. How many rows, comma, how many feature columns?
Exactly right. If a senior engineer says, I have a shape of 10,000 by 5, they aren't casting a spell. They just mean 10,000 examples with 5 details each. It's literally just a grid. It's just a spreadsheet.
Okay. So we have this massive spreadsheet. We have our features on the left and our label on the right. Now, here is where it gets really interesting to me from an engineering perspective. If I want to teach this machine to predict house prices, do I just feed it the entire 10,000 row spreadsheet and say, go memorize this?
You absolutely do not. And this is by far the biggest, most catastrophic mistake beginners make. Think about it. If you give the model every single piece of data you have to study, how do you know if it actually learned the underlying patterns of real estate or if it just perfectly memorized the answers?
It's the difference between truly understanding calculus and just memorizing the answer key in the back of the textbook.
Exactly. If a student purely memorizes the textbook, they will get 100% on the practice questions in class. But if you give them a brand new question on the final exam, a question they have never seen before, with slightly different numbers, they will completely fail. We call this overfitting in the industry. It means the model fits the training data way too perfectly, so it completely shatters when it hits the messy real world. We have to actively prevent the model from cheating.
So how do we actually do that? Do we cut the spreadsheet in half?
We split the data, yes. We take our 10,000 houses and we divide them up into 3 distinct buckets. And this is standard, mandatory practice. You will do this exact split in every single ML project you ever touch.
Walk us through the 3 buckets. Let's start with the biggest one.
The first bucket is the training set. This is the official study material. We give this massive chunk to the model, we show it both the features and indeed the labels, and we let it learn. This is usually the biggest piece of the pie, say 70 or 80% of your total data.
Okay, so it spends hours studying those 8,000 houses. It figures out that bigger houses usually mean a higher price tag. What's the second bucket for?
The second bucket is called the validation set. Think of these as the mock tests you take halfway through the semester.
Like a practice exam to see if you're actually getting it.
Yes. While the model is in the process of learning from the training set, we pause it every once in a while and say, okay, stop studying for a second. Here are 1,000 new houses from the validation set. Predict the prices for these. We check to see how well it does. If it's doing terribly, we intervene and change the fundamental settings of the model. We tweak what we call the hyperparameters. We actively use the validation set to guide and steer the learning process.
So the model does technically see this validation data during the process?
Indirectly, yes. We, the engineers, use the results from the validation set to manually tune the model's architecture. So the model inevitably becomes somewhat biased towards this specific validation data. It's like a student taking the exact same practice test over and over again. Eventually, they get really good at that specific practice test, but maybe they still don't fully grasp the broader subject.
Okay, so if we've used the training set to study, and we've used the validation set to tweak and tune our settings, we still need a true, unbiased final check.
The most important bucket of all, the test set. This is the final unseen end-of-year exam. We take these last 1,000 houses and we practically lock them in a digital safe. The model is never, ever allowed to see them during the training phase, not a single peek.
Why so secretive? I mean, data is valuable. Why waste 1,000 perfectly good examples by locking them away?
Because this is our one and only reality check. After all the training is completely done, after all the hyperparameter tuning on the validation set is finalized, we pull out the test set. We feed only the features to the model and we demand predictions. Since the model has truly never seen these specific houses before, if it actually gets the prices right, we know with high confidence that it has learned the general rules of the housing market.
It essentially proves that it can generalize to the real world.
Precisely. Generalization is the holy grail. If you do not have a pristine, clean test set, you are flying completely blind. You have absolutely no idea if your model will actually work when you deploy it live to your customers.
This directly leads to a concept I saw in the industry notes called data leakage. And honestly, that sounds incredibly messy.
It's significantly worse than messy. It's a career-ending mistake. Data leakage happens when you accidentally, usually through a coding error, let some of that secret test set information leak into the training set. Imagine if a careless teacher accidentally left the answer key for the final exam written on the blackboard while the students were supposed to be studying.
Well, every single student gets an A+.
Everyone gets an A+. You think you have a class of absolute geniuses. You confidently run to your boss and say, "Hey, my new AI model creates perfect predictions. We are going to make millions." You launch the product into the real world, but then it completely fails. It faceplants because it didn't actually learn the complex pattern of real estate. It just secretly saw the answers beforehand.
Can you give me a really concrete, maybe subtle example of this? Because leaving the answer key out on the desk seems so obvious. How does an entire team of smart engineers let this happen in the real world?
Oh, it happens constantly. Here is a classic terrifying medical example. Let's say you're trying to predict if a patient has a highly specific, rare disease based purely on their medical records. You train the deep learning model. It comes back with 100% accuracy.
Amazing.
Right. Nobel Prize worthy.
Very suspicious.
Yeah.
Nothing in biology or medicine is 100% accurate.
Right. So a senior engineer digs into the data, and they realize that in the raw spreadsheet, there is a seemingly harmless column labeled Patient ID. And they realize that 2 years ago, the hospital decided that any patient formally diagnosed with this specific disease was immediately given a new ID number starting with the prefix 99 because they were physically transferred to Wing 99 for specialized treatment.
Oh, no.
Oh, yes. The highly advanced AI didn't learn a single thing about medical symptoms. It completely ignored the blood pressure, the age, the blood work. It just mathematically realized, oh, if the ID starts with 99, then output's sick.
If not, output health. That's the leakage. The ID number was a massive clue that simply wouldn't exist for a brand new patient walking in the front door of the clinic. A new patient doesn't have a 99 ID yet because they haven't been diagnosed by a doctor yet.
Exactly. You accidentally gave the model information from the future information that logically only exists after the prediction event has already occurred. And the absolute second a new undiagnosed patient comes in with a normal ID number, the model completely fails to flag them. If you ever see a model that has 100% accuracy in training or significantly higher accuracy than top human experts, your immediate reaction should be deep suspicion. You almost certainly have a data leak.
That is a huge, huge takeaway for anyone listening. If it looks too good to be true, you probably accidentally showed it the answers. So assuming we didn't cheat, we've trained the model properly, we've kept our test set locked in the safe, now we finally run the test. How do we actually score it? Because saying it worked is a bit vague for engineering. We need cold, hard numbers.
We absolutely need metrics. And the specific metric we use depends entirely on what kind of problem we are actually solving. Let's go back to our two main problem types. First up, regression.
Remind the audience what regression means in this context.
Regression simply means we are predicting a continuous number, like the house price, or tomorrow's temperature, or the future value of a stock. Anything where the final answer is a fluid quantity.
Okay. In regression, you can't really talk about accuracy in a simple pass-fail percentage way, can you? I mean, if the house is actually worth exactly $500,000 and the model predicts $500,001, is it technically wrong?
Technically, mathematically, yes. It's not the exact number,
Yeah.
but practically speaking, it's a perfect prediction. No one cares about a $1 difference in real estate. So using a binary right or wrong label doesn't work here at all. Instead, we have to measure distance. How far off was our guess from reality? To do this, we use a very famous metric called mean squared error, or MSE.
Let's break that phrase down word by word. Mean squared error.
Start from the very back of the phrase, error. The error is just the raw difference between the model's prediction and the actual true price. If I predicted the house was $400,000 and it actually sold for $500,000, my error is negative $100,000.
Okay, simple subtraction.
Right. Now the middle word, squared. We take that error number and we square it, we multiply it by itself.
Why on earth do we do that? Why not just take the average of all the raw errors? Why make the numbers so massive and complicated?
For two highly specific mathematical reasons. First, to completely get rid of negative numbers. Think about it. If I overprice house A by $10,000 and I underprice house B by $10,000, the simple average of positive 10 and negative 10 is exactly 0.
Oh, right. It makes it look like the model made absolutely no mistakes on average.
Exactly. It looks perfect, but it actually made two significant mistakes. Squaring any number, positive or negative, makes the result positive. So the errors compound instead of canceling each other out.
That makes perfect logical sense. What's the second reason?
Second, and this is crucial for the way the AI learns, squaring severely punishes big mistakes.
Explain how that works in practice.
Let's use small numbers. If my model is off by $2, 2 squared is 4. That is a tiny mathematical penalty. The system barely cares. But if I am off by $10, 10 squared is 100. The penalty doesn't just grow linearly, it grows exponentially. We want to mathematically scream at the model for making massive catastrophic misses, but we really don't care as much if it makes a bunch of tiny, insignificant errors. MSE forces the model to prioritize avoiding huge blunders.
Wow. Okay. And then the first word, mean, just means we take the simple average of all those squared penalties across the entire test set.
Exactly. So a lower MSE number means the model's guesses are generally much tighter to the real, actual values. It's grouping closer to the truth.
Okay, that handles numbers perfectly. But what if we are doing the other major type of problem? Classification.
Classification is a whole different beast. This is when you want to put things into distinct, rigid categories. Cat versus dog. Spam versus not spam. Fraudulent transaction versus safe transaction. Here, we aren't predicting a fluid number, we are predicting a discrete class.
So in this specific case, we actually can ask, did it get it right or wrong?
Yes, absolutely. And the most basic, intuitive metric for this is accuracy. If you hand the model 100 emails, and it correctly identifies 90 of them as either spam or safe, you have a 90% accuracy rate. It's very simple.
It is simple, but I feel like there's a massive but coming here. You have that specific tone right now.
There is always a but in data science. Relying purely on accuracy could be terribly, dangerously misleading in the real world. Let's do another thought experiment. Imagine you are building that AI to detect a rare form of cancer from medical scans. And let's say this cancer is extremely rare statistically. Only 1% of the population actually has it.
Okay, so if I have a room of 100 random people, 99 of them are perfectly healthy, and exactly one person is sick.
Right. Now, what if I am a terrible engineer and I write a completely dumb program? Literally no AI involved, just one single line of Python code that just outputs no cancer for every single person who walks through the door, regardless of their scans or symptoms. What is my mathematical accuracy?
Let me think. Well, out of the 100 people, it would be absolutely correct about the 99 healthy ones. So mathematically, it has 99% accuracy.
99% accuracy. You can put that on a billboard.
Yeah.
But it's a completely useless garbage model. It completely missed the one single person who actually needed medical help. It provided zero clinical value. In fact, it's actively dangerous because it gives a false sense of security.
Wow. Okay, that really puts a phrase like 99% accuracy into stark perspective. You can lie with statistics incredibly easily if your data is skewed.
That is exactly why in classification problems, especially when dealing with rare events like fraud or disease, which we call imbalanced data sets, we need much deeper, more nuanced metrics like precision and recall. We rely heavily on a tool called a confusion matrix.
I genuinely love that name, the confusion matrix. It sounds like a sci-fi movie about my life.
It sounds super complex, but it's literally just a 2x2 grid that shows exactly how the model is getting confused. It clearly separates the types of errors. It answers the question, did we accidentally call a healthy person sick? That is a false positive. Or did we accidentally call a sick person healthy? That is a false negative.
And in the real world, those are two profoundly different types of mistakes with totally different consequences.
Absolutely. Think about it. If Netflix recommends a terrible movie to you that's a false positive, it's slightly annoying. You lose 5 minutes of your life before you turn it off. The cost of being wrong is practically zero. But if a self-driving car's AI fails to see a pedestrian crossing the street and firmly believes the road is empty, that's a false negative. It's an absolute tragedy.
So the stakes dictate the metric.
Exactly. The confusion matrix helps us specifically tune the model to avoid the most expensive, most dangerous mistakes. For a spam filter, we might explicitly tell the model, look, I really don't care if you accidentally flag a few safe newsletters as spam, but do not, under any circumstances, let a phishing virus through to my inbox.
I love that framing. It's not just about trying to be right overall. It's about intimately understanding exactly how and where you're wrong.
That is the absolute essence of model evaluation.
Okay. We have covered an absolutely massive amount of ground today. We've formally defined the hierarchy AI to ML to DL. We've looked at the two main learning styles, supervised versus unsupervised. We've broken down the anatomy of data into features, labels, and those crucial train, validate, test splits. And we just covered scoring with MSE, accuracy, and the confusion matrix. I want to synthesize all of this into a single, clean mental image before we jump into our final translation drill.
Let's draw the line. This is the mental flow diagram that every single listener should ideally have permanently burned into their head right now.
Walk us through it left to right.
Step 1. Input. You take your raw features, the area, the rooms, the location.
Model. You feed those exact features into the black box, the mathematical pattern machine.
Prediction. The model processes the inputs and spits out a numeric guess, like the price.
Comparison. You take that guess and you compare it directly to the actual value, which is your label from the historical data.
Error. You mathematically calculate the difference using your chosen metric, like MSE.
So it's features go into model, model makes prediction, then compare prediction to actual, which gives you the error.
That is the core loop. Every single thing in AI, from the absolute simplest linear regression model predicting house prices, all the way up to the most complex large language model generating code, follows some version of that exact flow. It predicts, it compares to reality, it finds the mathematical error.
Okay, now that we have this solid mental model built, let's prove that it actually works for our listeners. It's time for the translation drill.
This is genuinely my favorite part of the deep dive. Let's see if we can decode the industry jargon.
Here is how we are going to play this. I am going to play the role of the nervous junior developer, or maybe the non-technical hiring manager who doesn't quite know the heavy tech jargon. You, the expert, are going to look down your nose and say a scary, jargon-filled sentence that you might hear in a brutal technical job interview or read in an advanced research paper. I am going to try to decode it into plain conversational English using everything we just learned today.
I am ready. I'll make them sound as pretentious as possible.
It was born ready. Hit me with the first one. Let's see what you got.
Expert sentence number 1. We trained a regression model on 10,000 samples with 8 features.
Okay, let me break that one down piece by piece. First, regression means we are actively predicting a fluid number like a price or a temperature, not sorting things into categories. 10,000 samples means there are exactly 10,000 rows in our giant spreadsheet that's our M variable. And 8 features means we have 8 columns of clues or inputs that's our M variable. So the plain English translation of your sentences. We showed the computer 10,000 historical examples, we gave it 8 specific details about every single one, and we asked it to mathematically learn how to predict a specific numeric value.
Perfect translation. You nail the regression part, predicting a number. That is usually where beginners trip up and confuse it with classification. Ready for sentence number 2?
Let's go. Hit me.
Expert sentence number 2. To ensure robust generalization, we split the dataset 80-20 for training and testing.
Okay, the split. This is the school exam strategy we talked about. Translation. We let the model study 80% of the examples to find the patterns, but we totally hid the remaining 20% in a safe-to-use as a final unseen exam, just to make absolutely sure the model wasn't just blindly memorizing the textbook answers.
Spot on. And that word generalization is key. It's the fancy academic word for learning the underlying concepts instead of just memorizing the specific examples. It proves the model actually works on data it hasn't ever seen before.
Got it. Give me another one. Make it a bit trickier.
Expert sentence number 3. The model achieved 92% accuracy on the validation set during the first epoch.
Ooh, okay. First, accuracy instantly tells me this is a classification problem.
Oh.
We are sorting categories like spam, not predicting prices, and validation set means this isn't the final locked-away exam.
Yep.
Translation. Out of every 100 predictions it made on the halfway mock test while it was still actively learning and tweaking its settings, it got exactly 92 of them correct.
Exactly right. And notice how you specifically said mock test, because I deliberately said validation set. That is a massively crucial distinction in the industry. If I had said test set, that would mean the final official score before deployment. Validation explicitly means we are still actively in the lab tuning the knobs.
I am really getting the hang of this. Let's do one more. Make it the hardest one.
All right, expert sentence number 4. We detected significant data leakage in the pre-processing pipeline, resulting in artificially low mean squared error.
Oh man, okay, leakage, that's the cheating one. And mean squared error means we are back to regression, predicting numbers, and low error is supposed to be good. So, translation. Oops. We totally messed up our code and accidentally let the model see the future information or the answers to the final test while it was still studying, so it cheated. Our incredibly good-looking results are completely fake, and we basically have to throw it away and start over.
A+, my friend. That is exactly what that sentence means in the real world. And honestly, if the folks listening right now can truly understand those 4 specific sentences, they are already miles ahead of 50% of the people pretending to know AI on LinkedIn.
It's amazing how much less scary all of this is when you just strip away the Greek letters and visualize the basic spreadsheet and the school analogies.
That is the whole secret to the industry. It's absolutely not magic. It is not a black box of wizardry. It is just data flowing into pattern extraction, followed by rigorous evaluation.
So what does this all mean for our listeners today? We've successfully built the what. We know exactly what the engine looks like. We know the parts. But there's a massive piece of the puzzle still missing.
There really is. Today, we confidently talked about the model learning patterns. We casually said it mathematically adjusts itself. We said it actively tries to minimize the error. But we never actually said how it does that.
Right. How does the machine actually know which way to adjust its internal dials? If the predicted house price is too high, how does it physically know which variable to blame and change? Does it blame the square footage? Does it blame the bedroom count? Does it blame the zip code?
That is the cliffhanger. That is where the actual magic trick happens inside the black box.
Next time, in our next deep dive, we are going to open up the hood and look at the engine running. We are going to thoroughly discuss loss functions and the single most famous, most important algorithm in all of modern AI, gradient descent.
It's literally the algorithm that runs the modern world. It is the complex mathematical equivalent of trying to walk down a steep mountain while completely blindfolded, just by feeling the slope of the ground under your feet.
I really love that imagery. We are going to learn exactly how the system reduces its mistakes, step by mathematical step.
It's going to be a really good session.
But for today, before we wrap up, we want to leave you with a small, practical homework assignment, a call to action.
Yes. I want you to look at a regular problem in your own daily life. Maybe it's managing your monthly budget, estimating your morning commute time, or even planning your diet, and try to formally describe it using the terms features and labels. If you want to predict, will I be late for work today? That is your label. What are the features you need in your spreadsheet? Is it the amount of rain, the exact time your alarm went off, the day of the week?
That is a fantastic mental exercise. We want you to write your specific examples in the comment section below. We really want to see how you are applying this new mental model to the real world.
And if you have any questions at all, if anything we said about the M&N shapes or the concept of data leakage was still a bit confusing, just ask us down there. We read all the comments.
Absolutely, we're in there answering them. And of course, if you found real value in this deep dive, if you feel even just a little bit smarter than you did 40 minutes ago, please smash that like button, share this video with a colleague or friend who is also trying to learn AI without the dense math, and make sure to subscribe to the 60 Seconds Academy channel so you absolutely don't miss that next crucial lesson on gradient descent.
It's going to be a deep one.
Until then, keep analyzing the data patterns around you.
And keep learning.
See you next time.